To define the concept of parallel worlds, one must first engage in a rigorous semantic and geometrical analysis of the term itself. In the strictest mathematical and physical sense, parallelism implies a state of non-intersection. Two parallel lines, extended infinitely into Euclidean space, will never meet. Therefore, if we apply this definition to the cosmological concept of a world, understood here as a distinct continuum of space-time or a separate causal reality, a truly parallel world is one with which we have absolutely no points of contact. If a world is parallel to ours, it exists in a state of total isolation relative to our observational capabilities. We cannot see it. We cannot touch it. We cannot exchange information with it. If there were a surface of contact, a bridge, or a wormhole connecting our reality to theirs, the definition of parallelism would immediately collapse. They would no longer be parallel. They would be intersecting or tangent. Consequently, to discuss the search for extraterrestrial intelligence or alternative habitats for life within the framework of scientific inquiry, we must reformulate our terminology. We are not searching for parallel worlds, which are by definition inaccessible and empirically unverifiable. We are searching for other worlds. This linguistic shift is not merely pedantic. It fundamentally alters the methodology of astrophysics. By classifying them as other rather than parallel, we acknowledge the possibility of interaction, however faint or distant that interaction might be. We open a bridge of perception. We acknowledge that these worlds, while separated from us by vast gulfs of vacuum and light years of distance, exist within the same overarching physical framework. They obey the same laws of thermodynamics, gravity, and electromagnetism. Because they share this physical reality, they emit signals, photons, gravitational waves, neutrinos, that can, with sufficient technological sophistication, be intercepted and analyzed by instruments constructed on Earth. The history of our attempt to bridge the gap between our world and these other worlds is a narrative of improving optical resolution and shifting paradigms. It is a history that began not with radio telescopes or space probes, but with the human eye straining against the blurring effects of Earth's atmosphere. We must look back to the latter half of the 19th century to understand the genesis of the modern search for extraterrestrial civilization. This period, specifically the era surrounding the Great Opposition of Mars in 1877, marks the moment when the other world of Mars ceased to be a mere wandering point of light and became a landscape of projection for human hopes and fears. The central figure in this early chapter of planetary exploration was the Italian astronomer Giovanni Schiaparelli. Working from the Brera Observatory in Milan, Schiaparelli utilized the modest technology of his time to map the surface of the red planet. It is crucial to understand the limitations of 19th century astronomy. There were no CCD sensors, no adaptive optics to correct for atmospheric turbulence, and astrophotography was in its rudimentary infancy. Observations were conducted visually. The astronomer would stare through the eyepiece for hours, waiting for fleeting moments of stillness in the atmosphere, moments of good seeing, where the shimmering image of the planet would stabilize for a fraction of a second. In those split seconds, the brain would attempt to integrate the visual data into a coherent image. Schiaparelli recorded a network of linear structures crisscrossing the Martian surface. He designated these features with the Italian word canale. In Italian, canali can refer to natural channels, straits, or grooves, geological features formed by non-intelligent processes. However, when this term migrated across the linguistic barrier into English, it was transliterated and translated as canals. This translation carries a heavy semantic load. A channel can be a riverbed carved by erosion. A canal is an artificial construct, a feat of engineering designed and executed by an intelligent agent for a specific purpose. This linguistic nuance ignited the imagination of Percival Lowell, a wealthy Bostonian mathematician and astronomer. Lowell was a man of significant means and intellectual intensity. Driven by the conviction that Schiaparelli's canali were indeed artificial waterways, Lowell dedicated his life and fortune to proving the existence of a Martian civilization. He funded and constructed the Lowell Observatory in Flagstaff, Arizona, choosing the site for its high altitude and clear, dry air, factors that optimized seeing conditions. From the late 1890s through the early 20th century, Lowell produced intricate maps of Mars. He saw not just lines, but a coherent global network. He theorized that Mars was a dying, drying world, an aging planet where an advanced, desperate civilization was channeling meltwater from the polar ice caps to the arid equatorial regions to sustain their agriculture. For Lowell, the observation was not a hypothesis. It was a visual certainty. He observed the canals changing intensity with the Martian seasons, which he interpreted as the seasonal growth of vegetation along the waterways. This period represents a unique intersection of science and mass psychology. For decades, the existence of a Martian civilization was considered a plausible, if debated, scientific reality. However, as optical instruments improved and the rigorous standards of the scientific method were applied more stringently, the consensus began to shift. By roughly 1915 to 1917, the majority of the astronomical community concluded that the canals were not real features. They were optical illusions, a product of the human brain's tendency toward pareidolia, the psychological phenomenon where the mind perceives a specific, meaningful image in a random or ambiguous visual pattern. When the eye strains to see detail at the limit of resolution, the brain connects the dots, creating lines where only separate dark patches exist. Despite the skepticism of the professional community, the romantic idea of a living Mars persisted in the public consciousness, and even in some scientific circles for much of the 20th century. It was not until the dawn of the space age that the canal hypothesis was definitively buried. The final punctuation mark on the era of romantic speculation was placed by the robotic emissaries sent from Earth. While the American Mariner 4 mission in 1965 provided the first grainy, crater-filled images that dispelled the notion of a lush civilization, the Soviet Mars 3 mission is also of profound historical significance. Mars 3 was the first spacecraft to achieve a soft landing on the Martian surface. Although its transmission failed shortly after landing, the very fact of its arrival, a human-made artifact resting in the desolate red dust, signaled the transition from remote speculation to direct contact. The reality of Mars was revealed to be a cold, irradiated desert, devoid of cities or irrigation networks. Yet, the absence of macro-scale engineering projects did not end the search for life. It merely shifted the focus from biology and sociology to chemistry. The search for extraterrestrial intelligence, or at least extraterrestrial biology, transitioned into the search for biosignatures. We ceased looking for architects and began looking for metabolites. In the contemporary search for life on Mars and other worlds, methane has assumed a central role. Methane is a simple hydrocarbon, but its presence in a planetary atmosphere is thermodynamically significant. On a planet like Mars, with a thin atmosphere dominated by carbon dioxide and subjected to intense ultraviolet radiation from the sun, methane is unstable. UV photons break the chemical bonds of the methane molecule, initiating a chain of photodissociation that destroys the gas over a relatively short geological timescale, typically a few hundred years. Therefore, if we detect methane in the Martian atmosphere today, there must be an active source replenishing it. There are two primary mechanisms for methane production. The first is geochemical, a process known as serpentinization, where olivine and pyroxene minerals in the planetary crust react with liquid water and heat to produce hydrogen, which then reacts with carbon to form methane. This process, while abiotic, requires liquid water and geological activity, which are themselves indicators of a dynamic environment. The second mechanism is biological, methanogenesis. On Earth, the vast majority of atmospheric methane is produced by living organisms, bacteria and archaea in wetlands, oceans, and the guts of animals. For years, the detection of methane on Mars was elusive and controversial, hovering at the very limits of sensor sensitivity. However, modern missions have revolutionized this pursuit. The ExoMars Trace Gas Orbiter, a joint mission between the European Space Agency and Roscosmos, is equipped with spectrometers of unprecedented sensitivity. These instruments operate by analyzing the spectrum of sunlight passing through the Martian atmosphere. Different molecules absorb light at specific, characteristic wavelengths. By measuring the absorption lines, scientists can determine the composition of the atmosphere with extreme precision. The sensitivity of these modern instruments is difficult to overstate. We are no longer speaking of percentages. We are speaking of parts per billion, or even parts per trillion. To visualize this, imagine a distinct grain of sand in a volume of sand filling an Olympic swimming pool. The TGO is capable of detecting methane at these infinitesimal concentrations. Recent data has confirmed the presence of methane spikes, transient plumes that appear and dissipate. This suggests that Mars is not a dead world, but a dormant one, puffing out gases from subsurface reservoirs. Whether these reservoirs contain colonies of methanogenic microbes or strictly geological reactions remains one of the most compelling questions in modern planetary science. While Mars has long monopolized the attention of exobiologists, our gaze has recently turned toward our other neighbor, Venus. If Mars is the freezing, desiccated corpse of a planet, Venus is its hellish counterpart. In terms of size and bulk composition, Venus is Earth's twin. Yet, their evolutionary paths diverged catastrophically. Venus stands as a cautionary tale of planetary evolution gone wrong. The surface of Venus is obscured by a permanent, opaque shroud of clouds composed primarily of concentrated sulfuric acid. Below these clouds, the atmosphere is so dense that the pressure at the surface is 90 times that of Earth, equivalent to the pressure found 1 kilometer beneath the ocean. The temperature hovers around 460 to 500 degrees Celsius, hot enough to melt lead. This state is the result of a runaway greenhouse effect. At some point in the ancient past, Venus may have had oceans, but as the sun grew brighter, the water evaporated. Water vapor is a potent greenhouse gas, trapping heat and causing more evaporation, creating a feedback loop that eventually boiled the planet dry and baked carbon out of the rocks, forming a thick carbon dioxide atmosphere. It seems counterintuitive to search for life in such an environment. However, the Soviet Venera program, which successfully landed a series of probes on the Venusian surface in the 1970s and 1980s, provided data that continues to be analyzed. These landers, engineering marvels designed to survive the crushing pressure and searing heat, operated for only a brief window, typically roughly an hour, before succumbing to the environment. They sent back panoramic images of a yellow-tinged, fractured landscape. While the surface is almost certainly sterilized, scientific attention has shifted to the upper atmosphere. At an altitude of approximately 50 to 60 kilometers above the Venusian surface, conditions are surprisingly Earth-like. The pressure drops to 1 atmosphere, and the temperature is manageable. It is here, in the temperate zone of the sulfuric acid clouds, that some researchers speculate microbial life could exist, floating as aerial plankton. This hypothesis gained sudden traction with the controversial detection of phosphine in the Venusian atmosphere. Phosphine is a toxic, foul-smelling gas. On Earth, it is produced almost exclusively by industrial processes or by anaerobic microbes living in oxygen-starved environments. The detection of phosphine via radiotelescopy suggested a potential biosignature. If non-biological chemistry cannot explain the presence of phosphine, and current models struggle to do so, then the biological hypothesis remains a valid, albeit tentative, avenue of inquiry. It forces us to reconsider the definition of a habitable zone, extending it from the surface of a world to its atmospheric layers. Moving further outward beyond the asteroid belt, we encounter the gas giants. For a long time, Jupiter and Saturn were considered hostile to all forms of life. They are composed mostly of hydrogen and helium, lacking a solid surface, and are bathed in lethal radiation belts. Jupiter's magnetosphere is a particle accelerator of terrified power, trapping charged particles that would strip apart complex molecules. However, the focus of astrobiology in the outer solar system has shifted from the giant planets themselves to their retinues of icy moons. Europa, one of Jupiter's Galilean moons, presents one of the most promising environments for extraterrestrial life. Paradoxically, Europa lies far outside the Sun's traditional habitable zone. Solar energy at this distance is too weak to maintain liquid water on the surface. Indeed, Europa's surface is a shell of hard, water ice, frozen to the temperature of rock. Yet beneath this crust lies a global ocean of liquid water, containing more than twice the volume of all Earth's oceans combined. The energy source maintaining this liquid state is not solar, but gravitational. As Europa orbits Jupiter, it is caught in a gravitational tug-of-war with the other large moons, Io and Ganymede. This orbital resonance forces Europa into an elliptical orbit. As it moves closer to and further from Jupiter, the immense gravity of the giant planet stretches and squeezes the moon. This constant physical deformation, known as tidal flexing, generates friction within the moon's rocky core. This friction dissipates as heat, hydrothermal energy that melts the ice from below. We believe that on the floor of Europa's dark ocean, hydrothermal vents may exist, similar to the black smokers found on Earth's ocean floor. On Earth, these vents support rich ecosystems entirely independent of sunlight, deriving energy from chemosynthesis. If such vents exist on Europa, they could provide the chemical nutrients and energy gradients necessary for life to arise and persist in the eternal dark. A similar narrative applies to the Saturnian system. Saturn, the ringed jewel of the solar system, hosts Enceladus, a small moon that actively vents plumes of water vapor and organic molecules into space. The Cassini spacecraft flew through these plumes, sampling their composition and confirming the presence of complex hydrocarbons and salts, essential ingredients for life. Enceladus, like Europa, possesses a subsurface ocean kept liquid by tidal heating. Then there is Titan, Saturn's largest moon. Titan is a world of eerie familiarity. It is the only moon in the solar system with a substantial atmosphere, dense, nitrogen-rich, and hazy with orange smog. It has a full hydrological cycle, but the fluid involved is not water. On Titan, it is too cold for liquid water. Water ice there is as hard as granite. Instead, liquid methane and ethane rain from the clouds, flowing into rivers and pooling in vast polar lakes. Titan represents a natural laboratory for prebiotic chemistry. It raises the question, could life exist based on a completely different solvent? Could there be methanogenic life forms that use liquid hydrocarbons instead of water as the medium for their biological processes? If so, Titan expands the definition of habitability to include biochemical architectures radically different from our own. Leaving our solar system entirely, we enter the realm of exoplanets, planets orbiting other stars. The discovery of exoplanets has been the most significant astronomical development of the last 3 decades. We have moved from knowing of 0 exoplanets to cataloging thousands. The methodology for finding these worlds relies on indirect inference. The most prolific method is transit photometry. When a planet passes in front of its host star, it blocks a tiny fraction of the star's light. By monitoring the brightness of a star over time, astronomers can detect these periodic dips. The depth of the dip tells us the size of the planet. The frequency tells us its orbital period. Another method, radial velocity, measures the wobble of a star caused by the gravitational pull of an orbiting planet. As the planet orbits, it tugs the star back and forth, causing a Doppler shift in the star's light. The light shifts toward the blue end of the spectrum as the star moves toward us and toward the red as it recedes. By analyzing these shifts, we can determine the planet's mass. The ultimate goal of exoplanet research is not just detection, but characterization. We are developing techniques to analyze the atmospheres of these distant worlds. When a planet transits its star, a small portion of the starlight passes through the planet's atmospheric rim before reaching our telescopes. The gases in the atmosphere imprint their spectral absorption lines onto this light. By isolating this signal, we can detect water vapor, carbon dioxide, methane, and potentially biosignatures like oxygen and ozone. But we also look for technosignatures, specific manifestations of intelligent activity. In the vastness of the cosmos, an advanced civilization might modify its environment in ways that are detectable across interstellar distances. We look for the spectral signature of industrial pollutants, such as chlorofluorocarbons, which do not occur naturally. We look for the thermodynamic waste heat of megastructures. A civilization that captures a significant percentage of its star's energy, using a hypothetical Dyson swarm, would inevitably radiate waste heat in the infrared spectrum. An excess of infrared radiation from a star system, seemingly inexplicable by natural dust, could be a fingerprint of high technology. The history of searching for such signals is fraught with false positives. The human desire to find patterns, the same impulse that led Lowell to map canals on Mars, complicates radio astronomy. A classic example occurred in 1967 with the discovery of pulsars. Jocelyn Bell Burnell, a graduate student at Cambridge, detected a radio signal pulsing with incredible regularity, every 1.33 seconds. The signal was so precise, so artificial in its consistency, that for a brief time the research team jokingly labeled it LGM1, standing for Little Green Men. However, further analysis revealed that the source was not a broadcast, but a natural object of extreme physics, a neutron star. A neutron star is the collapsed core of a massive star that has ended its life in a supernova explosion. When a massive star runs out of nuclear fuel, its core collapses under its own gravity. The collapse is halted only by neutron degeneracy pressure, a quantum mechanical effect where neutrons resist being packed closer together. The result is an object with the mass of the Sun, but compressed into a sphere only about 20 kilometers in diameter. A teaspoon of neutron star material would weigh billions of tons. Due to the conservation of angular momentum, as the core collapses, its rotation speed increases dramatically, much like a figure skater pulling in their arms. These stars can spin hundreds of times per second. They also possess incredibly strong magnetic fields that funnel beams of radio waves out from their magnetic poles. As the star spins, these beams sweep across the cosmos like the light of a lighthouse. If Earth happens to be in the path of the beam, we detect a pulse each time the star rotates. The civilization turned out to be a cosmic clock, a dense remnant of stellar death. This discovery serves as a reminder that the universe is often far stranger and more energetic than our initial hypotheses suggest. We must also consider the possibility that advanced civilizations might not be broadcasting at all. The assumption that an intelligent species would expand outward, colonizing the galaxy and filling the radio spectrum with noise, might be a projection of our own current historical trajectory. There is a hypothesis that advanced civilizations might evolve inward rather than outward. If a civilization achieves the capability to upload consciousness into a digital substrate, their resource requirements would shift from physical territory to computational power and energy. Such a civilization might encapsulate their star to harvest energy and live entirely within a virtual reality of infinite complexity. To an outside observer, such a civilization would be silent and invisible, appearing only as a strange infrared excess, a star shrouded in a Dyson sphere, keeping its energy for itself. They would have no need for the rest of the universe. This brings us to the evolution of worlds themselves. The universe is not static. It is a dynamic, evolving process. Elements heavier than hydrogen and helium, the carbon in our cells, the oxygen we breathe, the iron in our blood, were not created in the Big Bang. They were forged in the nuclear furnaces of stars and scattered into the cosmos by catastrophic events, supernova and the collisions of neutron stars. We are, in a very literal sense, made of stardust. The evolution of life is inextricably linked to the violent evolution of the cosmos. Catastrophes, often viewed as purely destructive, are also engines of evolutionary acceleration. On Earth, mass extinctions caused by asteroid impacts or volcanic events have reset the biological clock, clearing ecological niches and allowing new forms of life to emerge. The extinction of the non-avian dinosaurs allowed mammals to rise from obscurity. Without that catastrophe, the evolutionary path to human intelligence might never have opened. Thus, the history of life is a dialogue between stability and chaos. Finally, we arrive at the ultimate boundary of our understanding, time itself. Science fiction often posits time travel as a mechanism for correcting mistakes, for returning to the past to alter the future. But the physics of time, governed by the laws of general relativity and thermodynamics, presents formidable barriers. The second law of thermodynamics states that entropy, disorder, always increases in a closed system. Time has an arrow defined by this increase in entropy. To reverse time would be to unbreak a glass, to unscramble an egg. Moreover, the causal paradoxes, such as the famous grandfather paradox, suggest that linear time travel would violate the logical consistency of the universe. If you were to travel back and prevent your own existence, you would not be able to travel back, which means you would exist, which means you would travel back. This loop collapses causality. Some theories suggest that such a paradox might be resolved by the creation of branching timelines, parallel worlds in the true sense, where every choice creates a new, divergent reality. But as we established at the beginning, such parallel worlds would be forever inaccessible to us. We are left, then, with the universe we occupy, a universe of other worlds, waiting to be found. From the methane plumes of Mars to the acid clouds of Venus, from the ice-covered oceans of Europa to the silent spin of neutron stars, the cosmos offers a reality far more complex, terrifying and beautiful than any fiction we could invent. We continue to look up, scanning the sky for a signal, a shadow, or a spectral line that will tell us, finally, that we are not alone.